Give me like a whole case of Snickers walking out of Sam's Club. It's like, what are you doing with those? Nothing.
Going to caramel.
Okay, lesson 33. It's factors of polynomial functions, graph of polynomial functions. It's really just kind of going back and seeing what we can observe from an equation and what it tells us about the graph. Okay, so that's kind of what we're going to go through, is just kind of go through, talk about what we know based on looking at equations and how it relates to the graph. So the degree of a polynomial. Okay, so degree of a polynomial can tell you how many humps or turning points a graph can possibly have, no more than one less than the degree. So first of all, when we talk about the degree of a polynomial, what's the degree?
The highest power.
The highest power, right? The term that has the highest power is your degree. And that tells you, notice it says how many humps, turning points. We could also think in terms of mins and maxes. Okay, those humps that we talk about are your mins and maxes, no more than one less than the degree. So in other words, if it is degree 5, then that means there are at most,
4 minutes.
right, okay, so, or I guess specifically 4 turning points, at most for 4 turning points, okay? Irreducible quadratic factors, like x squared plus 4, okay? Something like x squared plus 4 will never cause a polynomial to equal 0. Something like x squared plus 4 would always be above the x-axis, okay? So that would never equal 0. The graph of a polynomial crosses the x-axis when a real linear factor, such as x minus 2, occurs an odd number of times. So do you remember talking about that? We would have talked about that in pre-cal. But yeah, so it crosses the x-axis when it has an odd power. So something like x minus 2 would cross at x equals 2 as long as it's raised to an odd power. The graph of a polynomial does not cross when a real linear factor occurs an even number of times. It just touches. So that would be the location of a min or a max, if that's the case. Okay, so as we look at these, we've got to think about crossing versus touching. They both still count as zeros, whether it crosses through or whether it just touches it and turns and goes where it comes from. But just the difference of cross versus touch. So example 1 here. If f of x, you can see the equation, I don't need to read it. If f of x equals that, at what value of x does the graph of f touch the x-axis? At what value of x does the graph cross the x-axis? And what is the degree of f? So we need to know places that touch the x-axis. We need to know places that cross the x-axis. And in the end, we will talk about the overall degree.
So is finding the degree, would that be just as easy as taking, like, there's an exponent of 4 and 3 and 2, and since multiplying, you just add them together?
To an extent, yeah. I was going to save it to talk about the degree at the end, but yeah.
That was the one that jumped out to me.
Yep. Yep, we'll talk about that here. And I guess we could go ahead and talk about degree if you wanted to. I mean, degree, ultimately the degree is if this is all multiplied out, right? What is the highest power of x? Now, do you want to multiply this all out to find the degree? No. I have zero desire to multiply that all out. That's a lot of extra work for nothing. Okay, I'd rather just miss the degree, I think, at that point. But, so, what do you notice in terms of powers? This x has a power of 1, x plus 2 has a power of, what's x plus 2 have a power of? 4. So if you multiply that out, it'd be x to the 4th. What about x squared plus 3?
That's 2.
Has a power of 2, right? X minus 5 to the 3rd, that's going to be an x to the 3rd. X minus 7 to the 2nd is going to be an x to the 2nd. So to get the overall degree, yeah, you'd be adding all of those. 1 plus 4 plus 2 plus 3 plus 2 puts us at 12. So yeah, the degree is that easy. Just make sure you pay attention to all factors of x, right? And what would the, if we're multiplying this out or if it's just as is, what would be that power of x? Okay. Thoughts? What do you know about x plus 4?
It's got a power of 1.
Has a power of 1. So what's this going to do?
It's going to cross.
Okay. We're going to cross the x-axis there. At what value are we crossing the x-axis? Right. Solve that, set it equal to 0 and solve it. So we're going to cross the x-axis at x equals -4. What about x plus 2?
So it occurs 4 times, so it just touch.
Okay, it has an even power, so it's going to touch. So we're going to touch the x-axis at x equals -2. What about x squared plus 3?
It occurs once, so that they are going to cross. But is there a catch in this instance? It's squared, so you have to take it over the square root.
Well, there is a catch here. The factor x squared plus 3 occurs once, but that x squared plus 3 is not a linear factor. Okay, it is also a, where do we talk about it? Irreducible factor. Okay, an irreducible quadratic factor, x squared plus 3 is not going to cause the polynomial to equal 0. So it's not going to cross or touch. We get to ignore it. And here's the deal, guys. If you take x squared plus 3 and set it equal to 0 and try and solve it, you're going to have square root of a negative number, so you're going to have an I. And so that's why we're not going to talk about that one. Okay, x minus 5 to the 3rd, what are we going to do there? It's an odd power, so it's going to cross. We're going to cross at x equals 5. X minus 7 quantity squared. It's going to touch because it's an even power, so it's going to touch at x equals 7. I think, did we answer all the questions? At what value of x does the graph touch the x-axis? At what values does the graph cross the x-axis? And what is the degree? I think we got everything in there. Okay, questions there. That technically is a pre-cal review.
Yeah.
It's, it's not anything new or anything there. Okay, if you guys have what you need here, I'm going to scoot my screen up. Guess I probably should have asked that question, waited a moment before I just erased the screen, but.
So you know you understand it.
Oh, I forgot the graph isn't down here, dang it. Oh well. Okay, let me erase. I think I might have been a little bit more concerned if it was a harder topic. It wasn't a topic I was too concerned about. So, okay, example 2. Which of the following graphs most resembles the graph of y equals x minus 1 squared x plus 2 squared? So without using the calculator is the idea here, of course. Okay, obviously the calculator can check you, but the idea is, which graph is this? Just based on looking at it.
So it's a degree of 4. which means it would have 3 mins and maxes, which means that the first 2 can't be right.
Okay, so degree of 4, well, now,
It's a
It means
positive number.
At most, they could be.
yeah. Okay, so it is degree of 4 because it's power of 2 plus power of 2. Technically, it says at most 3, 1 less than that mins or maxes. So at most 3 mins or maxes. So technically, it could have less than that. But there is something, do you guys remember end behavior? We haven't talked about it. We're getting ready to talk about it more here in a moment. But end behavior, think about if it's x squared. What do you know x squared graphs do? They either go up, up, or down, down, depending on the situation. They don't go up, down, or down, up. Okay? Degree 2 is an example of an even power. All even powers fit that category, right? All even powers are either up, up, or down, down. If this is degree 4, then that automatically is going to eliminate A and B for that purpose because they have up, down behavior. Does that sound familiar? When we actually talked about that a little bit in Algebra 2. We hit it more in pre-cal, but so then that takes you to C and D. And what do we know at C and D?
We have to use zeros and such.
Yeah. X minus 1 squared tells me this is going to
Potential.
touch at x equals 1. And x plus 2 squared is going to tell me it's going to touch at x equals negative 2. So at that point, it puts us at D. And honestly, you could have used that information right there, the fact that it touches and doesn't cross. You never really had to find the degree 4. However, even if Ross hadn't said degree 4, I was going to talk about it because it reminds us of up, up, down, down behavior. Okay? Just remember if it's an odd power, like I always, even powers I correlate to x squared because you guys are very comfortable with a graph of x squared. Odd powers I correlate to x cubed because you are pretty comfortable with x cubed. That's either going to be down, up, or up, down. Okay, example 3. Which of the following functions is most likely to produce this graph? This invisible graph that you can't see. Okay, so again, this is without punching all those lovely things into your calculator. This is just looking at, okay, f of x, g of x, and h of x. Thoughts on maybe what we can talk about here?
Has to be an odd degree, right?
Has to be an odd degree because I have what I would call up and down behavior, right? So it has to be odd degree, which if it has to be odd degree, what can we eliminate? G of x can be eliminated because it's an even power, an even degree. What type of in behavior does this even degree have?
There are 2 negatives and a positive, right? So blah, blah.
Well, just look at what the lead coefficient is.
Okay,
So it's x to the 6, which is the even power. So that tells me up, up, or down, down. The negative coefficient tells me it would be down, down. Okay, kind of like a negative x squared. So g of x is out for those reasons. So that takes me to f and h, which are both still odds.
Would it be h of x plus negative x?
How'd you say that again? I think you had it.
Because the negative reflects it.
Right. Yeah, so this f of x equals x to the 7. That is odd, but the key is it's a positive x to the 7th. And a positive x to the 7th is going to start down and end up. if you think about the positive x to the third graph. So my graph does not do that. My graph starts up and ends down. And this right here, because we have an odd power and a negative out front, I have like negative x to the third, that is why h of x does work. Okay? And do note, it did just say most likely to produce this graph. Okay, it's not, necessarily exact or anything. It's just the being able to identify the shape. So definitely importance, as we talked today, about being able to identify, okay, is the degree odd or even? Is it a negative coefficient or a positive coefficient? Okay, questions there? Okay, next page. A cubic function is of the form f of x equals ax cubed plus bx squared plus cx plus d. When we say cubic, what needs to come to mind here?
The squiggle.
Squiggle thing. And it's a power of 3, right? Okay. Now, a cubic function can have either one inflection point only or one inflection point and 2 turning points. Because keep in mind, a cubic function is going to be a power of 3, right? So that means it has at most 2 turning points. With that in mind. Okay, so the x to the third you're used to looks like that, right? That's the x to the third you're used to, where my inflection point then is at your like 0, 0 idea. So that's the idea of one inflection point. Can you visualize one inflection point and 2 turning points? That's where you're going to end up with a min and a max. I should say that the other way. A max and a min. And you're going to have that inflection point in the middle. Okay, those are your options. If you just have the x cubed term and maybe the d term, no other x terms, it's going to look more like the first. If you have the x squared and x terms, that's when you start pulling the mins and maxes. Okay, that's when you get the humps in there. So now, a is negative versus a is positive. What's that mean there? What are my options? Because we're just going to put some sketches in here of what my graph could look like.
It's either going to be reflected or
Be reflected or be normal? Yeah. If a is negative, basically these two graphs would be flipped. In other words, they would start up and end down. And it could be like that with just an inflection point, or it could be more like that where there's an inflection point and 2 turning points. Or in other words, a min and a max. Okay? And keep in mind, a min and a max always have to occur in pairs. So you're never just going to have one turning point in a situation like this. If a is positive, well, those would be the ones I just drew. I just don't like how I just started to draw. What am I doing? I'm putting an extra curve in there. So if a is positive, it starts down and ends up. Okay, so you have some ideas there, right? A quartic function. What's quartic mean? Right. Quartic, we are talking about a power of 4, or a degree of 4. A quartic is of the form f of x equals ax to the fourth plus bx cubed plus cx squared plus dx plus e. There are many options for these graphs. So generally speaking, if a is negative, what do we know? It'd be down, down, right? Now, the basic x to the fourth graph, without the middle x terms, is a wide parabola. That should be flatter along the edge, not lopsided like that, but a basic x to the fourth. If you just graph y equals x to the fourth on your calculator, you're going to get a parabola that has a wider base. Okay? Now, what can happen though?
There can be turning points, mins and maxes.
Yeah. There can be turning points and mins and maxes. Now, keep in mind, if it's, for this to work out, you're going to end up, in order to keep the down-down behavior, you're going to end up with 3 turning points, or 3 mins and maxes. You can have the kind of M look. You can kind of have the more lopsided look. And that lopsided look could go either way. And I think, is there anything else I usually talk about? Those are the basic ones I talk about. Okay. In other words, that, the M look can be very uneven either way. Now, if A is positive, it's going to be up, up. And instead of M's, we're going to be talking about W's. Those W's could be somewhat symmetric. They could also be very not symmetric. And interesting to look at sometime is if you graph on your calculator y equals x squared and y equals x to the fourth, you can kind of see the difference about, I probably did that back in pre-cal for you, would be my guess. Sorry, my calculator was still on fall break, I think.
He's not ready to wake up. But...
Something. Oof. Yeah. Believe it or not, if you're looking up at my screen, my blue is my parabola, my y equals x squared. It goes out wider, but it also has that skinnier base. My red is y equals x to the fourth. And if you zoom in a little bit, you can kind of see, so there's the parabola, there is the quartic. So
it's more squared off.
Yeah, more squared off, which I feel like I did that better here where A is positive. I tried to square it off more. I got lopsided over here on my -1. But and again, when you throw in the x terms, that's when it starts pulling the various mins and maxes there. Okay. Well, next topic when you're ready. Now, notice the bottom says sketch the graph. So this is one of these where we're going to do this without the calculator. Okay, so the average value of all the roots of a polynomial. Okay, so this is average value of all the roots of a polynomial is x bar equals -b over NA. And that is x bar, so just like a little bar over it. Okay, so A and B come from your polynomial. So A being the coefficient of the highest power, and then B being the coefficient of the next, what should be the next highest power, whether it's there or not. Okay, and N being your biggest power, so basically your degree. In a quadratic, x bar is the x value of the vertex, because in a quadratic function, a parabola, your center of your graph is your vertex. So that is your average value. In a cubic function, which we just looked at. X bar is the value of the inflection point. Okay, because the inflection point is considered the center of the graph. In a quartic, X bar just gives us a good idea of the center of the graph. Okay, in other words, the higher the power they get, it just gives you a good idea of the center. It doesn't give you necessarily a specific point. So, with that information in hand, we're going to sketch the graph of y equals negative x cubed plus 3x squared minus 2x plus 3 by hand. Now, we've done a lot of sketching by hand when we're provided zeros, but we're going to do this a little differently this time. Okay? So, obviously, I just introduced the idea of x bar, didn't I? So, guess what we're going to use? We're going to try and use x bar here. So, x bar is negative of b over NA. We should probably go over here and talk. What do we know about this equation? It what? Right? What shape is this going to be? What type of graph is this?
Cubic.
It's a cubic, yes? So if this is a cubic graph, what does that tell me n is? N is 3. Because that's the biggest power, right? What is A?
It would be negative 1.
A is the coefficient of your x cubed term, so A is negative 1. B is 3. So B has to be, if A is the cubic, then B has to be the coefficient of the x squared. While we're at it, C is going to be negative 2, and D is going to be 3. Okay. Let's go ahead and find x bar. Negative of B over NA. So negative of 3 over 3 times negative 1. Did I get that right? So we just found x bar to be 1. Based on the fact that this is a cubic graph, what do we know?
It's the value of the inflection.
Right. We now know part of our inflection point, yes? Our inflection point is going to be 1 comma something. How do I find something?
Well, now that we have an x term, do we have to plug it back in there and solve for y?
Yep. Now that we have an x term, we can just plug it back in. So y equals the negative of 1 cubed plus 3 times 1 squared minus 2 times 1 plus 3. So negative 1 plus 3 minus 2 plus 3. And we end up with 3. So now we know that our inflection point is 1, 3. Okay, so we have an inflection point of 1, 3. We know this is cubic. What kind of behavior can we tell since this is cubic?
So it's a cubic of negative, so it would have to be up, down.
It's a cubic with a negative coefficient, and so that does tell me that this is going to be up-down behavior. I agree. There's only one other thing that.
And since we have a bunch of the stuff added up in the middle, does that mean we would have the turning points, not just the straight thing?
Yeah, and we can, because there's x squared and x terms, and I forget, there's one of those definitely terms that tells me, but x squared and x are both there. So that you can pretty much know that this is going to have the inflection point plus 2 turning points. Something else that will help you here, know that your y-intercept is always easy to tell in this form. Right? Does that sound familiar? Right here, because this 3 is at the end, and basically you can put 0 in for x, right? You put 0 in for x, we're going to get a y-intercept of 0, 3. Well, based on the fact that my y-intercept is 0, 3, and I have an inflection point at 1, 3, that right there tells me something weird is going on. So, I am ready to sketch a graph here. And put all of our information on here that we know. Oh, I should have before I did that. Some marks on there that I know I need. I mean, I know I need to go be able to go at least right 1 and up 3. So right now, I know I have an inflection point at 1, 3. You can label that IP if you want. We have a y-intercept at 0, 3. So somehow we have these 2 points. We have to go through both of them and they're side by side. Okay. We talked about what kind of end behavior. Yeah, we know there's going to be, and this is something, if I was doing this on my own, I would normally just kind of draw it in like in pencil, the fact that, okay, I'm going to have up and down behavior, right? Like that's, I would just kind of, if I was doing this on paper, just kind of, okay, there's my visual. Are you starting to see how this comes together? We're going to have to start high. We're going to have to go through this y-intercept of 0, 3 at some point. The question is, do we curve before or afterwards? Well, notice we have to go through 0, 3. We have to have an inflection point at 1, 3. So if that inflection point is at 1, 3, that's kind of the center of our graph. Are you visualizing what's going to happen here? If this is the center of my graph, that means I'm going to have a max to the right of it and a min to the left of it, which means between 0, 3 and 1, 3 is my min. And so as I draw this, I would start high, I would come down and go through there, and I would have something like that maybe. If it was easy to find an x-intercept here, we might, but this isn't going to necessarily lend itself to finding an x-intercept very easily. And again, it's just a sketch of the graph, right? We're not getting fancy here. This is just a sketch. There's always the option to then graph it on the calculator and see, what kind of craziness it looked like. Questions there? Okay. Problem set 33 is homework.